video channel. I hope you are happy and healthy, and today we are introducing the bridge course for the class 11 students. So we are going to start the first chapter of this bridge course, that is some basic concepts of chemistry. So this covers all the basics of the chemistry. Make sure you watch the complete bridge course series. I am Pooja Vaishnav, your chemistry mentor. I am pretty sure that you are ready to watch. So let's dive in.
So let's begin with the chapter known as some basic concepts of chemistry. Okay. So what is the first topics we have is matter. So what is matter? Matter is anything which has mass and occupies the space. Example, listen. This is a pen, right? It has a mass. Yes, we have a mass, and I can see it is also occupying a space. So can I call it as a matter? Yes, for sure. Similarly, book, water, air, all these has a mass and it is occupying the space. So it is known as matter. A very simple thing. So again, this matter is classified into two different types. In a two different way we have categorized. What are those? Physical classification and chemical classification. Physical classification means physically we have classified. Okay. Generally we see the three physical states. What are those? Solid, liquid and gas. Right. So we have the physical classification are made like this. Physically they are classified as physical classification, that is solid, liquid and gas. Here you can see the solid, liquid and gas. This is the physical classification. Based on physical state we have classified. Correct. Then what is this property? If we look into the property, we know that solid has a definite shape. Yes, it has a definite shape. Does it has a definite volume? Yes, it has a definite volume. So it has a definite shape and it has a definite volume. I am just writing S and V. It has a definite shape and it has a definite volume. If we come to liquid, what about liquid? Does it has a definite shape? No, it doesn't have a definite shape, but it takes the shape of container. See, if I have two glasses of water, its shape is different. Consider the shape of the glass is completely different. If I pour the water, it is going to take the shape of that container. It is going to take the shape of that glass. Correct? So, liquid doesn't has its own shape, but it takes the shape of container. Clear? What about volume? It has a definite volume. For sure, it has a volume. What about gas? Gas doesn't have a definite shape and no volume. Clear? Okay. Now we will move on to chemical classification. This matter are classified chemically. They are, in the next slide we'll move and we'll explain there. Okay. So, chemical classification. Chemical classification. Chemically, they are classified into two major types. That is pure substance and mixture. This pure substance is again classified as two major types. That is elements and compounds. This mixture is classified as homogeneous mixture and heterogeneous mixture. Okay. So these elements are again classified as metals, non-metals and the last one metalloids. Okay. So what is this? Pure substance. What is pure substance? Generally, pure. When do we use this word pure? Generally with the water. Pure water. We used to drink pure water. Why do we call it as pure? Because in that we have only H2O molecule. If I add anything other than H2O, can I call it as pure? No, I can't call it as a pure water. See, clear? So in the pure substance, I should have only one type of particle. One type of substance, molecule we can say. Okay. Pure substance, it should have only one type of particles. But in the mixture, how do we make a mixture? See, juice. We every day used to drink a juice, right? To make a juice, we used to take a juice extract. To that, we used to add water and sugar, right? These are the different substance we are adding. Okay. So juice is pure, water is again pure, and sugar is also pure. All these are pure. There is no any impurities are present in here. And when this pure mix it together, I got a mixture. Clear? So now this juice which is prepared from all this is known as mixture. It is not known as a pure substance. Clear? Okay. If we come to the classification of, that is, elements and compounds. Generally students used to confuse in between this. Elements is having always a single one type of particle. Always. But what about compounds? It has many different types of elements are involved there and it forms a compound. You know, have you heard a term atom? Atom is the simplest unit present in the matter. Okay, the matter, atom is the simplest unit present, general, right? So you consider I have a eraser. Okay, in this I have many different particles, correct? In that particles, in each small pieces I can see many more atoms, right? So similarly, elements in what is the meaning of element? Elements has only one type of particle. It can be atom. They are generally atom. Clear? They are generally atoms. So in the periodic table, whatever you see there, all those are elements. Like hydrogen, helium, neon, argon, all those are elements. Because in there I can see only one type of particle. They are generally atom. But what about compounds? Compounds are formed when atoms or molecules combine. When atoms or molecules combine, I used to get the compound. So what is the example for compound? See, H2O. How do we make H2O? By using hydrogen and oxygen gas. If I combine this, I am going to get a water, right? It is not balanced actually. Okay, now I got a water. So what is this now? This is a compound. What is this now? Here I can see two hydrogen element. Here I can see two hydrogen element, and even here I can see two oxygen elements. So what is this now? This is elements and this is compound. Now I hope you got the clear idea. Clear? Okay. What is this? Elements again classified as metals, non-metals and metalloids. Okay. Metals means you know. Okay. In the periodic tables, generally metals are placed at the where? Generally metals are placed here and non-metals at the corner, and here I can see the metals, non-metals this side and metalloids in the middle. Okay. Metalloids have a property in between metals and non-metals. So they are known as metalloids. Okay. Now we'll move on to the next part. Okay. The same thing they have given. Matter, then they are classified as pures and mixture. Then again they are classified into elements and compounds, and mixture are classified into homogeneous and heterogeneous. Okay. Now we'll come to fundamental units. What is this? Fundamental units are the units which can neither be derived nor be resolved into another units. What does it mean? Fundamental says it is not going to change. Whatever you do, it's not going to change. Listen, if I want to measure the height of anyone, what I'm going to use? I'm going to use a meter scale, right? I need a meter scale to measure the height. Similarly, if I want to see the weight of that person, what I have to use? I have to use a weighing scale that is in kgs, right? So every to measure anything we need some units. To measure the liquid we need liters. To measure temperature we need Kelvin scale, right? So these are the fundamental units which are like a standard. Okay. So let's move on and learn what is this. Here we have 7 fundamental units, that is mass, length, time, electric current, temperature, intensity and amount of substance. And if each of this quantity has its own SI unit. Okay. What are those? kg, meter, second, ampere, Kelvin, candela and mole. Okay. And these are the dimension. It is denoted by capital M and all, right? Okay. We'll move on to derived units. What are those? Derived units itself says derived. They are derived from fundamental units. They are the units which are derived from fundamental units. Let's see. Here I can see velocity. We know that the velocity is measured as distance per time. So distance is a fundamental unit. Time is a fundamental unit. So when 2 fundamental units we use here to get a new unit, that is velocity, which is measured in meter per second. Why? Distance is measured in meter and time is measured in second. So I got the unit meter per second. The symbol is this one, meter per second. What about this area? Area is measured as length into breadth. So meter square we used to have. What about volume? Length into breadth into height. All these are measured in length, meter, right? So this is something wrong. Printing mistake. Meter. Density, mass by volume. So mass is measured in kg and volume. We know that length into breadth into height. So meter cube. So kg per meter cube. Fine. Scientific notation. What is this scientific notation? See, when the scientific notation was not introduced, we had a very big problem in mathematical solving. See, we know that what is the speed of light? Do we know that? Yes, we know that the speed of light that is 3 into 10 power 8, right? So if this scientific notation was not introduced, in every calculation we needed to write 3 and 8 zeros. 1, 2, 3, 4, 5, 8. So this is something we needed to write always. So to overcome this, we introduced the scientific notation, which is a notation which is a proper representation of a number in exponential form. This is the exponential form. We have to write it in n into 10 power n form. See, this is n, capital N, and 10 power small n. So in this form, I can able to write any number and simplify it. Consider I have a number like this, many zeros. So if I want to, I can't able to write this number always in all the calculations. To simplify it, what I can do is I can write in a scientific notation form, that is 1.6 into 10 power. How much, what is the power? That we don't know. So decimal point is here, right? So 1, 2, 3, 4, 5, 6, 7. So I have crossed the 7 digits. So 10 power minus 7. Clear? 10 power minus 7. Okay. Minus 7 or plus 7? See, here the general confusion used to develop generally in the students. What is that? Students used to confuse which sign we have to put. Correct? So, see, the 1000 is written generally as 10 power 3. What is the symbol here? Plus. What happened here? Here we moved this decimal points towards right or left. It's about left. If we are moving towards left, we are going to use a positive sign. And if we are moving towards right, then we have to use negative sign. Here in this case even we are moving towards left side. So we are going to use positive sign. Let's solve this one. 232.508. It can be written as 2.32508 into 10 power how much? So we have shifted this decimal point 2 digits away. So 10 power 2 plus 2 or minus 2. Here we move towards right. So right side it means we have to use negative sign. Clear? Here we shifted in a left side, right? So we have to use a positive sign. What about here? 1, 2, 3, 4. So 1.6 into 10 power 4. Okay, 10 power 4. Again we move towards right side. So we are going to use negative sign here. Clear? You got a clear picture now how we can solve the scientific notation. Then comes significant figures, which is very important. Okay, what is significant figures? There are certain digits in the measurement plus one uncertain digit. Consider I told 2 of my students to measure the weight of the apple. I gave one apple and I told 2 students the same apple to take the measurement, to take the weight of this. Okay, so what they did, student A told the weight of an apple is consider the weight of apples or apple is consider it's a 100 gram. Okay, the weight of apple is 100 gram, not 100 gram. We'll take it in numeric decimal one. Okay, consider it is 92.4 grams. Okay, and B told the weight of the apples is going to be 92.0 gram. Okay, so this is the 2 measurement given. So what I can observe here is these 2 digits which is given by both are certain. I can call it as accurate. But this is something inaccurate or uncertain. So taking this number is known as significant figure. So we have set of rules to find out a significant for figures for all different numbers. So we are going to see the rules here. What it says, all non-zero digits are significant. It means any number which is non-zero, it should not be a 0, is going to be significant. What is the example? Let's take example. Take 1, 2, 3. Consider I have a number like this. So how many significant figures I have? Because all these 3 are non-zero. They are not 0. So we have 3 significant figures. Let's take another example. Consider I have 1.23 like this. Okay. So now the decimal point is here, but they are not saying anything about decimal point. They told if it is non-zero, it is going to be significant. So how many significance we have here? 3 significant figure. 0 preceding to first non-zero digits are non-significant. Okay. 0.001. In this case, what I see is this is only non-zero. This is the only number which is not 0. But all these 3 are zeros. So zeros preceding the non-zero digit. This is non-zero digit. The zeros preceding are not significant. They are not significant. So I have to consider only this one. So I have only one significant figure in this particular number. Zeros between two non-zero digits are significant. Let's take example for this. 3003. Now in this case, I have two non-zeros and two zeros in between. So if this is non-zero, this is non-zero, but these two are zeros, right? So how many significant figures I have now? 4 significant figure, because these two are non-zero but these are zeros. Similarly, it can be anything like 3, 0, 4. So how many significant figures here? Now I have 3 significant figures because this is non-zero, this is not, but in between non-zeros, if I have zeros, then also it is considered as significant. Clear? Zeros at the end or right of a number are significant provided they are on the right side of decimal point. Here I have a rule, and the terminal zeros are not significant if there is no decimal point. What they are saying is, if we have a zeros at the end, we have a zero at the end, and if it is after decimal point, if it is after decimal point, then it is considered as significant. So let's take an example. Let's take an example, that is 32.0. So what it is? Now this 0 is at the end and it is after the decimal point. So I can call it as significant. So 1, 2, 3. 3 significant figures I have. Let's solve the problem. I want all of you who are watching this video to pause the video and try to solve by yourself. Okay, to try to solve by yourself, so that, and later on you can check the answers. Okay, so this is the best way of learning. So how many significant figures I have? 3 significant figures, because all are non-zero. Here 2 non-zeros, but in between non-zero I have a zeros. According to rule, if the zeros are in between two non-zero, they are also considered as significant. So we have 4 significant figure. What about this? Here I have 3, because the zeros are at the end and after decimal point. So 3 significant figure. Here this is not non-zero, so we have to cancel out 2 significant figure. This is always non-zero, means this is always not significant. 10 power anything is non-significant. Do remember that. So we have only 2 significant figure. Here 1, 2, 3. 3 significant figure. Here 1, 2, 3, 4. 4 significant figure. Here 1, 2, 3, 4. 4 significant figure. Okay. Now let's come to the law of chemical combination. Why do we need to study this? This law is very, very important, because when we know that there are many chemical reactions used to take place, but we must know the basic rule of combination, correct? So let's learn the very 5 basic laws of chemical combination. What is this? Law of conservation of mass, law of definite proportion or constant composition, law of multiple proportion, Gay-Lussac's law of combining volumes, and Avogadro law. We have 5 laws which are going to be very, very important. So let's understand this one. Law of conservation of mass. The heading is itself saying conservation of mass. Conservation means there is no loss of mass. Where there is no loss of mass? In the chemical reaction. Consider I have a reaction like this. What it is? Consider I have a 2 reactant A plus B and I got a C as a product. So what I observe here is, consider the mass of A is 10 gram and mass of B is 10 gram, and I got the product, consider I have got a product 20 gram. So what I observe here is 10 gram plus 10 gram. The total reactant is 20 gram and the product is 20 gram. So mass of reactant and mass of product is completely equal. Here I can see there is no loss of mass in this chemical reaction. This is only what told by this law. Law of conservation of mass. No loss of mass during the chemical reaction. Clear? Okay. Now let's solve a problem on heating 25 gram of calcium carbonate CaCO3, which is 25 gram. On heating, I got 11 gram of CO2, 11 gram of CO2 and 14 gram of CaO is left. Which from data, which law of chemical combination is confirmed? Simple thing. What I have to do? I'm going to add this. And if I solve this, I am going to get 25 gram. So mass of reactant and mass of product is equal. So this is something told by law of conservation of mass. Law of conservation of mass. Okay. Law of definite proportion. This is given by Joseph Frost. What he states that a given compound always contain exactly the same proportion of element by weight. Okay, so he took a cupric carbon. He took one of a compound. In that, what he found is he took two samples, that is natural sample and synthetic sample. And what he find out that in that particular compound, the percentage of copper, carbon and oxygen in both is completely exactly same. Let's take one of an example. Consider I have taken a water. Okay, this water is brought. I have brought three samples of water from different places. It can be tap water, it can be lake water, it can be pond water. From wherever you bring three samples. And what I found, whatever from wherever the sources it can be brought, but in the water the composition, that hydrogen and oxygen is present in a definite ratio. In a definite ratio of mass they have combined. In which ratio? In the H2 I can see that. In the H2 I can see what is the mass, atomic mass of hydrogen? 1. I have 2 hydrogen plus what is the atomic mass of oxygen? It is 16. So 2:16. It means 1:8 ratio. In this ratio, this H2O is combined and I got a water. So from wherever you bring, the percentage of elements present in that particular compound is going to be exactly same. This is something told by Joseph Frost in this law. Clear? Okay. Now we'll move on to the next law, that is law of multiple proportion. When two elements combine with each other to form two or more compounds, the masses of one element which combine with the fixed mass of other elements bears a simple whole number ratio to each other. What you want to say is, consider when two elements combine with each other. See, hydrogen combined with oxygen and I got H2. This is one product. And same, if I take this, I am going to get H2O2 also. I can get two different products, right? So if I observe the ratio of this, what I am going to see is the ratio of this is going to be 2:16 here and here 2:32. Okay, so if I see the ratio, it is fixed. The hydrogen mass is fixed here. This ratio, if I see the ratio of this, that is 16:32. If I simplify this one, I am going to get 1:2. This is a simple whole number. This is a simple whole number, right? So what you want to say is, when two different elements combines, we get a new product. More than one compounds can form. More than two or more compounds can form. The masses of one element which combine with the fixed mass of other element. The masses of this element which combine with the fixed mass of other element is in the simple whole number ratio. These two oxygen is in simple whole number ratio with each other. This is told by John Dalton. Clear? Gay-Lussac's law. So now let's learn about Gay-Lussac's law of gaseous volume. The volume of reactant and product in a large number of chemical reactions, the gases are related to each other by small integer provided volume are measured at same temperature and pressure. Okay, what they have told, volume of reactant and product in large number of chemicals are related to each other. Okay, consider I have a Gay-Lussac's law of gaseous volume. What he says, it is developed by Gay-Lussac for sure. Okay. So what he says that the volume of reactant and product and large number of chemical reactions of gases are related to each other by small integers, provided volumes are measured at same temperature and pressure. What I want to say is, consider I have a reaction like this, H2 and O2. I combined it and I got a H2O, right? So here I can see that the ratio of this, okay, if I observe the ratio, when two volume of H2 and one volume of O2 combined, I got 2 volume of H2, correct? Similarly, if I take 10 ml of H2O, I should take 5 ml of O2, then I am going to get a 10 ml. So this number, the reactants and the products are related to each other by small whole number ratio, right? Here if I see the ratio, it is 2:1:2, right? This is a simple whole number ratio. This is only what you want to say. So they are related to each other in the ratio of small whole number. That's a simple thing. And what he told, and during the reactions the volumes are kept at same temperature and same pressure. No change in temperature and pressure is done. Okay. Now let's move on to the last law, that is Avogadro law. This is given by a great scientist, that is Avogadro. What he says that all gases contain equal number of particles under similar conditions of temperature and pressure. A simple thing what he told, consider I have a beaker like this, shaped vessel. Okay. To this I have in here I can see the nitrogen gas and here I have oxygen gas. So if these both are equal in shape, the volume is completely equal, then I can say that these both gas have same number of particles. Same number of particles are present in both. So what he says, whatever gas you take, if the vessel in which that gas is kept, if it is same, then number of particles in both is going to be same. But the condition is temperature and pressure should be in a same condition. Okay. So this is something which is told by Avogadro law. So now the last, that is Dalton's atomic theory. This is the theory made by Dalton about atomic structure, how the atom is. So what is this? It's all about assumptions of Dalton. What he says is atom is considered as a hard, is completely hard like a ball and is completely dense. Consider an iron ball. Okay, if you take an iron ball, which is very hard, right, and it is very completely dense, it has more density, right, and smallest indivisible particle of matter, and we can't able to divide it. Okay, it is indivisible of particle of matter. And what he says, it is indestructible. It cannot be destroyed or created. Atom can't be created and it can't be destroyed. Okay, atom is a smaller portion of matter which takes part in the chemical combination. In any chemical reaction, atom is He is only taking part in the reaction. Atoms combine with each other to form compound. Atoms or molecules in a simple whole number ratio. Generally, atoms combines and I get a molecule. Consider hydrogen. Two hydrogen atom combine to form a H2 molecule. And H2 combined with a chlorine, I got HCl. So what it is? These are hydrogen molecule, HCl compound, or a molecule we can go. Okay, they combine in a small whole number ratio. The simple thing, simple whole number ratio is there. Atoms of same element are identical in mass and chemical property. Say, see, consider I have a hydrogen element. Okay, in this I have a hydrogen atom. Obviously, I have a hydrogen atom. All the hydrogen atoms of that particular element is completely same. It has same mass and same chemical properties. A very simple thing. So you got a clear picture what is his assumptions. Clear? So this is the last, and part 2 is going to come in the next video. If you are new to this channel, do subscribe.